All right, so at the end of last video, this was on the page, just gonna talk about it real quick. Our radicals, just like exponents, will split across multiplication and division. We did that earlier. The book had this weird nested radical property. Like if you look, they changed them both into fractions. Fraction times fraction becomes 1/12. Honestly, I would just do it that way. Like memorizing this as a separate rule, writing it down on a formula sheet is not worth the effort. Yeah. If you ever run across nested radicals, writing them in the fractional form is the way you want to go. Because it probably won't be del calculus, and the fractional form is always better than the radical form. All right. So then we have this simplified form of a radical. These rules are extremely antiquated. They are a holdover from the 50s and 60s when we were putting astronauts into space and landing them on the moon when we didn't have handheld calculators. Because you should not grab a female coworker or a male coworker. But our calculators were people then. So here, the radicand has no factor other than 1 that is a perfect nth power. So all the exponents in the radicand must be less than the index, meaning anything under the root, the number of objects you have in there has to be less than whatever our index on the root is. I kind of think of that as the jailer. The jailer only lets out groupings that it likes. So if he's a 3 and there's only 2 of you, you ain't getting out. But if there's 4 of you, he'll let 3 of you out and the last one stays. So I know that's kind of a weird thing, but we will see it in action soon. No fractions in the radicand means no fractions inside a radical. But again, we have that quotient property. Radical splits across quotients. No denominator of a fraction may contain a radical. Again, this is an antiquated rule before we had calculators, but the process of moving a radical from the bottom of a fraction is sometimes useful for some of the crazy problems we ask you in pre-cal and calculus. So we're still going to cover it, but understand the having to write your answer that way is kind of silly. And a lot of the really pretty calculators, not expensive, pretty, will actually rationalize for you. It's really nice. And the exponents in the radicand may not share a common factor with the index. So this is if you have the 6th root of x squared, the 6 and the 2 are both divisible by 2. If you convert it back to a fraction, you have to reduce the fractional exponent to lowest terms. All right, generally the way you're going to see this though is you're going to have numbers in a radical and x to higher powers than the index of the radical. And so we're going to look for groupings that can come out of the root. All right, so I got a bunch of different problems here to practice this, and then we are going to continue to use this skill when we're adding and subtracting radicals. I do have a couple of these on the review for the test, for the midterm, which means, yes, it's going to show up on the test. All right, so let's look at 45 first. Let's zoom this in because we all know I write too big. So in order to figure out what's going to come out of a square root, square roots have an invisible index of 2, meaning I need pairs. You guys should be fairly used to that though. Like the square root of 9 we know is 3 because 9 is 3 squared. Squared square root cancel out. So what we're looking for is pairs of the same thing. So I'm going to break down 45 to the side. That's what I do with any number that I don't recognize right away. And it ends in a 5, so it's divisible by 5. And in fact, it is 9 times. Hey, there's that 9 I was just talking about, which is 3 times 3. Now, the way you write your work from here can look a number of different ways. So I'm going to do it kind of the quick way, and then I'm going to fill in the work that I'm talking through. So you guys can see it, but also see like what I kind of expect it to look like when you're more comfortable doing these. And again, if you have one of the fancy calculators that will reduce this for you, make use of your tools. So the pair of 3's is the same as 3 squared. The square root of a thing squared is just the thing itself. So the pair of 3's under the radical simplify to a single 3 outside the radical. just being multiplied to the square root. Anything that did not have a pair, which in this case is our 5, is the leftovers. 5 does not have a partner to break out of the radical jail, so the 5 is stuck inside still. Now, if everybody breaks out, you just have a square root of 1, which is 1. But most of the time, there's usually a leftover. All right, so the square root of 45 is the same as 3 square root 5. Now, as I said before, let me move that down, and then we're going to break it down more, and I'm going to write out what I said. But very often when I do these later on, I do the number to the side or any variables to the side, and then I write what the result is. So I talk through this more than I show it. So I just want you guys to be prepared for that expectation after these 5. All right. So here, 45 is the same as 3 times 3 times 5. Well, the 3 times 3 could be written as 3 squared. And then the square root can break across multiplication. So now I'm going to write it that way. The square root of 3 squared times the square root of 5. And there is our square root squared, cancel out, and that gives us the 3. And there's our square root of 5. If that does not make sense after you see multiple of these, please come to office hours. We can talk about it. I can try to find a different way to explain what's going on. But I use a lot of kind of weird shorthands to work through a lot of these. All right, cube roots. So just like square roots, we needed pairs, and most of the problems are just going to be square roots. But higher power roots will still work with this. So a cube root is looking for groups of 3 can come out and break out as a single. So something to the third that is cube rooted is the something. So 54 itself is not a perfect cube, and some of the fancier calculators, they don't always work so well simplifying higher power roots just because there's a point where the programming is tedious. But we're going to take 54 and break that down. So now it's even. 2 goes into the 5 twice, 14, so 27. If you're doing enough of these, you start to recognize some of the numbers. And indeed, check it out. We have 3 of a kind 3s with a leftover 2. It's kind of the same way I did earlier, the 3 of a kind 3s. That's the cube root of 3 to the third. That is going to break out as just a 3 on the outside of the answer. Then I leave some space for x's and y's that are probably going to come out because they usually do on these problems. And then I write the cube root and I write my leftover 2 inside. All right, now I have to consider x to the 13th. So that is 13 x's being multiplied, which means there are several 3 of a kinds in there. So we just have to figure out how many and how many are left over. Now the way I do this, I start writing, I'm going to write 13 x's, which is tedious. So after a while, I just put dots. So we're grouping by 3, so I'm actually going to write them like that. X, 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 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I see 1, 2, 3, 4. I have a 5-year-old, forgive me. 4 3 of a kinds. So that is going to come out as x times x times x times x. So that is 4 x's on the outside, which we write as x to the 4th. And then our leftover is going to stay here next to the 2. So now I have 3x to the 4th and the cube root of 2x. All right, now we just have to deal with the y's. There are 8 of them. Writing 8 y's is tedious. This is why I use dots. 1, 2, 3. I'll just put a red line there to be like, these are y's. 4, 5, 6, 7, 8. So those 3 y's are going to come out as y. These 3 also come out as another y. Y times y. We have a y squared on the outside. And left over y squared on the inside. So this is our simplified radical. I use quotes because it looks uglier, and we don't use this skill that often. It'll kind of maybe come up in calculus a little, but by the time you get there, hopefully you've been working with math so much, this part should feel a little easier. But if you're not going on, why do we focus on it? Don't have a good answer to that question. I often ask it and get weird looks from people because I ask it in the grocery store usually. When was the last time you factored? And the deli person is like, did you want cheese or not? Yeah, I know, I'm weird. All right, so now we've got just numbers. So this does equal some ugly decimal, but the question here is, can we write it as an elegant with smaller square roots? So back in the day before calculators, the square root of 15 was in the square root tables. It is a bigger decimal, but times 20 is not in the square root tables. So before calculators, you would look up radicals in tables, and it was calculated out to a whole bunch of decimal places, and you just use however many decimal places you needed. But then you're doing decimal math, which is pretty ugly quick. So if I can reduce this to a smaller radical, a smaller number, and then just an integer outside, multiplying the ugly decimal times an integer is much nicer than doing two ugly decimals. So together, they would merge into one square root. So it is the square root of 15 times 20, which is some number. I don't care what the bigger number is because that is not the answer. Yes, I know it's 300. I still don't care. I'm going to write over here for our breakdown 15 times 20, because that is the pair from whatever the bigger one is. And now we just need to break those down. So 15 is 3 and 5. 20 is 4 and 5. And that 4 is indeed a pair of 2s. So check it out. I have a pair of 2s and a pair of 5s. Now this 4 is not a terminal number, so it is not a leftover. It got split into two 2s, and now the 4 is not part of our end result. So the only leftover is the 3. So pair of 2s, 2 squared, square root of 2 squared is going to be a 2. Times pair of 5s, squared, square root comes out as a 5. Leftover, square root of 3. Square root of 3 was a much more familiar decimal back in the day, like 1.73, I think. Like, I'm not even that old and I still kind of remember the decimals. And then multiplying that by 2 times 5, which is 10. Ooh, nice. Way better than figuring out the decimals of the square root of 15, which you would have to do the square root of 3 times the square root of 5, and the square root of 20 reduce 2 times the square root of 5. So I'm just telling you the story in the hopes you appreciate the kind of pains that mathematicians had to go through before calculators, and the kind of amazement that we landed astronauts on the moon with this. But now, you carry around a calculator in your pocket. Despite what all the teachers in the past said, you're not going to have a calculator in your pocket all the time. Yeah, you are. All right. So now we have uglier mess. So it doesn't just have to be cube roots. Any kind of radical will work. So the 6th root means groups of 6. Now I also wrote this because sometimes people look at this and they're like, oh, parentheses, oh, I have to distribute. You have to distribute when there is addition or subtraction. There's no addition or subtraction. Like if one of the numbers was negative, we would have a negative number, but it's not subtraction. So this is all multiplication. I have 3 times the first ugly root times 4 times the second ugly root. The parentheses are just grouping them as 2 numbers, but it doesn't mean distribute. So what I'm going to do instead is rearrange, because 2 times 3 is the same as 3 times 2. I can swap my order of multiplication and be fine. So I'm going to group the 3 and the 4 up front. and then the other two radicals, which are both sixth roots. So I can actually group those under one radical. Y to the fifth times y to the 11th. All right, so now I have more normal looking exponents. You could convert these into fractional exponents and work the problem, and we may end up having to do that because I think we get a reduction in this, but this is the way I would normally track through the problem initially. So outside, 3 times 4 is 12. And then a sixth root of y to the fifth times y to the 11th. We count. 5 plus 11 is 16 y's. So indeed, those are both even, so we're going to need to see some reduction. So this can go one of two ways. I could reduce them first and then pull my groups out, or I could pull my groups out and reduce the end result. You will get the same answer either way, but because reducing first means I'm counting fewer things, I'm going to go that route. So that means I'm going to convert this into y. This is the sixth root, so it is a sixth fraction power. And then the other number is the top. So that is 16 sixths for the y. That reduces. 16 sixths are both divisible by 2, so 16 sixths is the same as 8 thirds. So that ugly mess is really the same as y to the 8 thirds. And in pre-cal and calculus, like that would be your answer. You'd write 12y to the 8 thirds and be done. But because we torture people for a living, apparently, Alex is not going to take that answer. It won't even let you do a fractional power. It gets pissy. All right, so there's 8 thirds of y's here. So I can think of this as 8 of them all raised to the 1/3. A group of 3 of them to the 1/3 would just be the thing itself, the y. So you can think of it that way. These are, you know, y to the 1/3 8 times, all side by side, or we can go back to the radical form and just think of 8 and group it by 3s, what's coming out, what's staying inside, which we actually just did earlier. So I am actually going to go with the write it weird way so you guys can see the different way of looking at it. You do not have to master all the ways. You simply have to master a way, be comfortable with it, and do it. I show you guys multiple ways in the hopes one of them clicks more. Seeing multiple ways can give you insights into different parts of the problem. All right, so 12. So y to the 8 thirds is the same as y to the 3 thirds, y to the 3 thirds, and y to the 2 thirds. So 3 thirds plus 3 thirds plus 2 thirds is 8 thirds. Or again, if you think of 8 thirds, that is an improper fraction. If you went back to a mixed fraction, it would be 2 wholes, 3 thirds and 3 thirds, those are wholes, and 2 thirds left over. So the 3 thirds are just first powers, so this is just y times y. That is a y squared on the outside. And the 12 still, so 12 y squared. And then the leftover is 2 y's inside a third root. So the cube root of y squared, which is the same thing we got here, a y squared outside and a y squared in the root. So there's that craziness where we see a reduction. Honestly, I never saw this until I was teaching this class, and like maybe in pre-cal when we talk about reducing radicals. That's it. Like I said, in calculus, they would convert it to the fraction 16 over 6. Oh, hey, look, it reduces 8 thirds, and that's where they'd stop. All right. This last one is 360. So you will have a couple of problems in your homework where they give you these big numbers. Break them down just like we did before. The 15 times 20 was actually a big number. It was just broken down in the first step. Now, it doesn't matter what pair, how you split the 360, just as long as you recognize which numbers are actually part of the end result and which are not. Because I've had students have that problem before where they're not sure where to stop and which numbers that they write down. So if it is a prime number that the only way you could split it is 1 in the number itself, that is one of your endpoints. If the number can be broken down into two numbers that are not 1, the product multiplying two numbers that are not 1, then you break it down more. So 360, hey, it ends in a 0. And I'm going to put the 10 first because I'm more comfortable with the 10. That is 10 times 36, and that 10 is 2 times 5. 2 and 5 are both prime, so those are terminal numbers. The 10 split into those, so we no longer have the 10 to consider. So right now it is 2 times 5 times 36. But now I'm going to take my 36 and split it. Most people see it as 6 times 6. Some people see it as 3 times 12. Either works. You will get the same result. There's many different ways to arrive at the same answer here. And it doesn't matter which way you go. It doesn't have to be the most efficient. If you like to take the number and just divide it by 2 and count how many 2's you divided by and then write that down, that's fine. That works. You'd eventually get down to 3 times 3 times 5 of 45. And you would have divided it by 2 3 times. All right, so 2 and 3 are also prime. So that is our stop. What we need to do now is find our pairs. So I have a 2 and another 2. So I like the colors here because then it can be like, oh, I got that taken care of. And let me write that down. 2 on the outside. All right. See the 5, there's not another 5. Oh, there was another 2, but there wasn't another 2. So those are both going to be leftovers, but I do have a pair of 3's. So I'm going to write that outside. And then our leftovers stay inside the radical. And let me just clean up the multiplication there. 2 times 3 on the outside is now 6. 5 times 2 on the inside is 10. And in fact, if you've noticed here the 36 and the 6 times 6, we could have just written 10 times 36 under the radical. The square root of 36 is 6. Write it up front, done. So you don't have to go through all of this. I just like it because this process always works. So if I don't see one of the nice perfect squares right off, I know I will still find it by doing all of this. Alrighty. There's the end of that one.